Hello friends, today we will be discussing a very basic concept of human physiology, and that is action potential. Before discussing the action potential, we need to know about the resting membrane potential. Now, in a cell, you can see a cell bounded by the plasma membrane and then the constitution of various ions inside and outside of the cell. So in a normal resting cell, what is the status? That is, sodium, it mostly stays outside the cell, and the major intracellular cation is potassium. Okay, and the resting membrane potential is nearly around minus 90 millivolts. This is the normal constitution around the cell, and this constitution is in part maintained by this channel, what we call as the sodium potassium ATPase. What it does is it pushes 3 sodium outside of the cell and moves 2 potassium inside the cell. So what it is doing? It is doing two things. One, it is maintaining this electronic configuration, that is, sodium is pushed out of the cell, and another thing is, since the number of positive charges moving across the membrane is not the same, more sodium is coming out of the cell and less of potassium is going inside the cell. So what happens? The inside of the cell tends to become more negative. That is what contributes to this negativity inside the resting cell. Okay, and when the cell is resting, important thing is, these ions, they cannot move inside or outside of the cell. Why? Because the channels which lead to their entry are closed. Okay, and the lipid bilayer of the membrane, it is a barrier to entry of sodium or potassium, any movement of these ions. So whenever these channels they open, they allow these ions to move in regards to their electrochemical gradient. Now what is electrochemical gradient? One thing is, sodium as such, if it were not charged, so what would be the tendency of sodium across this membrane? Obviously, since it is more on the outside, it would try to get inside the cell. Okay, simple, by means of a passive process, because it is low in concentration inside the cell and more outside. So sodium from the outside would just tend to move inside. Okay, and opposite would be the case with potassium. Potassium would like to move outside of the cell because it is more inside the cell. Now another thing is, these are charged particles, so opposites, they attract. So this sodium is also attracted by the negativity which is inside the cell. So there are two forces. One is the chemical gradient, that is also pushing sodium inside, and then the electrical gradient, because there is negativity inside, so sodium is attracted towards that negativity. So both these forces, they tend to move sodium inside the cell, but during the resting state, since no sodium channels are open, it cannot move inside. Okay, and potassium tends to go outside, and since no channels are open, potassium cannot go outside. So this is a resting state of a membrane. Now what happens during an action potential? You can produce an action potential by stimulating a nerve electrically, or by putting in some neurotransmitter, some drug, some hormone, something, some chemical entity which could lead to generation of an action potential. Now what happens during that action potential is, there is a small change in the potential difference across the membrane at some point. Okay, if it is to that degree that it can trigger an action potential, so an action potential will be generated. Now that potential difference is called as a threshold potential. Whenever that stimulation reaches the threshold, an action potential will be generated. If it is less than that, action potential will not be generated. So action potential becomes a all or none phenomenon. Okay, now what happens in the membrane? In the membrane, say there is, normally a membrane would be, everything will be negative inside and positive outside. Okay, if we stimulate a part of this, the polarity tends to change. So this region would become negative and this region may become positive. Okay, now this region leads to stimulation of one type of sodium channels, what we call as voltage gated channels. Voltage gated because they sense such changes in the potential difference, and when those channels they are activated, it leads to opening of many sodium channels, which leads to, now you know sodium has a tendency to move inside, so whenever it finds a channel open, it will be moving with a great force into the cell. And when that happens, what will happen? It is not only sodium, it is also a positive charge which is moving inside. So when it is moving inside, along with that, what will happen? This negativity inside will be converted into positivity. So if you plot a graph, what you will see is, say this is the resting membrane potential which was carrying on. Now we give some stimulus, and that stimulus incidentally reaches the threshold potential. When it reaches the threshold potential, there is opening up of so many sodium channels which are voltage gated, and it leads to a spike, a upstroke, a rapid upstroke, and then followed by a downstroke. Okay, and this downstroke goes even beyond the resting membrane potential, and then slowly it comes back again to the resting membrane potential. So this whole sequence of events is what we call as an action potential. Now this part is contributed by the sodium channels, voltage sensitive sodium channels, and when these channels open, very soon they get into a state of inactivation. And inactivation is what? If we look at the sodium channel, it has got, say this is a sodium channel, it has got two types of gates. One gate is present on the outside and one gate is present on the inside. Okay, now the outside gate helps to throw it open, and the inside gate, it helps in the inactivation of this channel. So what happens is, whenever a sodium channel is activated, the outer gate it opens up and it lets the sodium flow inside, and in a matter of a few milliseconds, the inactivation gate it goes into closure. It closes. So when it closes, what happens? No more entry of sodium can happen. So when this is closed, this channel is said to be inactivated. Inactivated means it cannot send more sodium inside, and also this cannot be thrown again into an open configuration unless it comes back to its original closed state. Okay, so this, when it is inactivated, and this part, this was rapid opening of the sodium channels. This, at this point of time, what happens, most of the sodium channels they go into a phase of inactivation, so it does not go further. And why does it go further? Because a lot of sodium ions are entering inside, and how much further it can go is decided by means of a very important concept, a very important equation, that is the Nernst equation. And the Nernst equation is what equates the electrical and the chemical gradient across the cell. So for sodium ions in this human cell, the Nernst potential is plus 65 millivolts, which means if the sodium channels are open, so much sodium will enter into the cell, so that the inside of the sodium, inside of the cell, it becomes plus 65 millivolts. So this potential might even cross 0 and make it towards the positive side. Okay. Now this, after this, the sodium channels are closed, so role of sodium channels is over. Now what happens is, at the same time when the threshold is reached, there is also opening of the potassium channels. Now potassium is where? Potassium is on the inside. Okay, and more on the inside and less on the outside. So the chemical gradient would be to move potassium out of the cell. Okay, but what about the electrical gradient? The electrical gradient is, since it is more on the inside, so potassium will have a tendency to stay inside the cell. It cannot leave that negativity. So these two forces more or less cancel out at the resting membrane potential. And the Nernst potential for potassium, it ranges around minus 95 millivolts, which is nearly equal to the resting membrane potential. So even if you have potassium channels open during a resting membrane, there will be no movement of potassium ions here or there. Okay. Now what happens? After this stage, since that was also, the threshold voltage was also a stimulus for opening of potassium channels, so the potassium channels open up. When they open up, what will happen? Now the cell has reached a positive potential, so there is now positivity inside. When there is positivity inside, the potassium will have a tendency to move outside depending on its concentration gradient. So potassium tends to move outside, and when it moves outside, it also takes positive charge. So what happens? There is a downfall of this potential down. Okay, and it keeps on going down and down. And the potassium channels do not have an inactivation gate like sodium channels. So the potassium channels, they tend to stay open for a long time. So the potential, it drops, and it goes to a state what we call as hyperpolarization. Okay, which might be even lower than the resting membrane potential, because potassium will tend to bring it around minus 95 millivolts, which is its Nernst equation potential. Okay, so then again, when all these things happen, the sodium potassium pump is again at work. So it pumps whatever sodium has entered into the cell, and the potassium is pumped back into the cell, and the normal constitution of the cell, it is restored. And this is how an action potential finishes. So how is it transmitted? It is very simple. As stated here, there is a negative potential at this part of the membrane, so it will be making small currents here. So small currents from here can flow. These currents will lead to negativity here, and then further negativity here, then currents will flow from here and negativity, then negativity. So this, whatever potential has been generated here, it will be transmitted all along the membrane up to the level of synapse, where a chemical transmission occurs. That will be discussed later on. Thank you so much.